Hello, I have a question for you. What would you think if you know, like, you are eating a credit card every day, or 75% of the plastics in the water are microplastic? Well, there's a solution for you. Microplastic remediation from the Chemical Engineering Department. I'm Hector Lustuno.
I'm Stephanie Gustafsson.
I'm Alex Chaffin.
I'm Lionel Duran.
Okay, first, let's define what microplastics are. Microplastics are any plastic smaller than 5 millimeters and none greater than 1 millimeters. Microplastic sources are from human consumptions, such as degraded plastics, cosmetics, and fabrics. Most sources end up in wastewater uh, that are pathways to drinking water and oceans. Removal techniques are unfortunately relatively new. And microplastics are a health hazard for living organisms, especially marine life, because they confuse microplastic with their regular food. Recently, there are found microplastics inside the fish. So our method, it's inspired by an Irish guy, Brian Ferreira, who developed a basic concept in 2019 Google Science Fair. Uh, the method consists in oil attracts the microplastic particles because they are non-polar, and introducing a ferrofluid, as you can see in the video, the microplastic and the oil mixture is magnetically removed in the water. Now, Stephanie will explain you about the solution.
Okay, let's take a look at our solution. We propose a tertiary process that will be added to wastewater and drinking water treatment facilities. Our goal is to remove 90% of the remaining microplastics in the effluent and drinking water. We will be using canola oil to attract the microplastics, but instead of using the magnetic separation technique, we chose to use a centrifuge to separate our oil and water mixture. This way allows our process to stay continuous. Our design is low cost, high efficiency, and uses environmental friendly materials. Now let's take a look at the specific placement of our add-on treatment design. To the left, you find a typical wastewater treatment process, where the primary and secondary treatments already remove up to 98% of all the microplastics. Our design would be added as a tertiary treatment option, where you can see the red arrow pointing, and focus on removing 90% of those remaining 2% to limit the pollution into the discharge. Studies have shown that due to the large flow rates, hundreds of microplastics per liter is still entering freshwater and oceans if no tertiary treatment is added. To the right, you find a typical drinking water process that removes between 70 to 80% of all microplastics. Our design would be added as a last step before the disinfectant, where the red arrow is pointing, to further clean the water before reaching the consumers.
Let's take a step-by-step approach to this process. The contaminated water enters our system where it is mixed with the canola oil. This mixture enters the centrifuge where the oil and water are separated. The oil, which now contains the microplastic, enters a flash drum, while the water enters one of two granulated activated carbon filters. These filters remove any trace amounts of oil and microplastics. The vapor oil stream exiting the flash drum is recycled, and the microplastics are discharged in the liquid oil in stream 8. We used Aspen to model our process, but had to make two assumptions. The first being that the centrifuge effectively separates the oil and water, and also all microplastics are leaving the system in stream 8.
Our design results are as follows. 99.35% of microplastics entering our system are removed. 96.51% of oil entering the flash distillation column is recovered. Using the flash saves us 88% in oil cost, saving over $45 million annually. The cost to build is about $1.1 million. The annual operating cost is a little more than $4.6 million. We concluded that the design was feasible. However, further pilot scale testing is needed to determine how the microplastics will behave in the flash distillation column to support our assumption that no microplastics leave the flash through the vapor stream. If it were found that microplastics do make their way back into the system through the vapor stream in the column, a possible solution could be adding packing to the column to prevent microplastics from making their way up. The group solutions to dispose of waste were between selling the contaminated oil to a biofuel company or our preferred solution of burning it to use as energy, resulting in lower operating costs, which is always a plus. Here we have a digital version of our poster. We would like to thank Dr. Herbert, Dr. Adriana Brush, and the University of Arizona Department of Chemical and Environmental Engineering. Bear down.
Thank you.
Thank you.